The physical universe operates as a chaotic, continuous flow of energy and matter. We observe this scale in the swirling gas structures of the Crab Nebula. We observe it on Earth, where supersonic fighter jets violently compress the atmosphere into localized vapor cones. A computer cannot process this continuous physical reality. A CPU operates strictly on discrete binary logic. It requires defined states, not flowing phenomena. To simulate the real world, we use governing equations. These act as a rigorous translation layer, converting abstract physical behavior into exact mathematical statements. We are going to systematically build a computational model from a blank mathematical void, piece by piece. To accomplish this, we have to strip away the visual noise of the universe. We must organize reality into 3 strict, independent layers of mathematical rules. The first layer consists of universal laws. These are the absolute rules of physics that apply everywhere, regardless of the material involved. The second layer defines the specific material. A fluid behaves differently than a solid, and these local properties require their own mathematical descriptions. The third layer establishes the physical geometry. To simulate anything, we must place rigid boundaries that lock the math into a specific spatial and temporal domain. When architecting a model, these 3 layers must be developed completely independently of one another. If you conceptually mix a universal law with a localized material behavior before structuring the code, the resulting simulation will output invalid data. A robust computational model requires us to strictly separate the unbreakable rules of the universe from the unique properties of the material we are studying. The most universal rule in physics is conservation. In any closed system, physical quantities, mass, momentum, or energy, cannot appear or disappear from the void. This schematic is the template for conservation, dictating how quantities evolve. The left side tracks local density over time. We balance this against the divergence of flux, measuring flow across boundaries. Finally, we add a source or sink term for generation or consumption. This exact mathematical structure tracks biological population densities in ecology, and it forms the basis of Euler's equations for gas dynamics. But a conservation law is a blank slate. It guarantees that our totals balance out, but it tells the computer absolutely nothing about how a specific material actually moves. To tell the model how things move, we define constitutive relations. These relations explicitly define the missing flux term, the J in our equation, based on the specific physical nature of the material. One common behavior is diffusion. At the microscopic level, particles collide randomly, naturally smoothing out sharp concentration gradients over time. We define this behavior mathematically using Fick's law. It states that flux moves strictly down a concentration gradient, acting as an automatic equalizer. Particles can also move with purpose. When dragged by fluid flow or gravity, we call this advection. Combining both mechanisms produces the advection-diffusion equation. Our model now simulates a particle undergoing random thermal motion while pulled by an external force. We owe our understanding of these equilibrium states to the foundational statistical mechanics developed by physicists like Ludwig Boltzmann. The vast diversity of physical phenomena we observe emerges directly from the precise coupling of these different constituent relations.
Capturing complex behaviors does not require drafting highly complex equations. This 3D cross-section illustrates Taylor-Harris dispersion, a prime example of macroscopic emergence in a fluid pipe. Injecting a dye droplet into this flowing water triggers 2 mechanisms. First, faster central fluid velocity violently stretches the droplet into a parabola. Simultaneously, molecular diffusion forces radiomixing. These 3D mechanisms collapse into a 1D model using an enhanced effective diffusion coefficient. We see this same mathematical simplification in biology, where models like Fitzhugh-Nagumo distill electrochemical storms in neurons into predictable reaction diffusion waves. Complex macroscopic reality emerges through the rigorous coupling of simple conservation rules and material behaviors, acting across different spatial scales. At this stage, our differential equations represent an infinite set of possible universes. To anchor the math to a specific physical reality, we apply rigid constraints known as boundary and initial conditions. This 2D heat grid demonstrates a Dirichlet boundary condition. We lock an edge to a fixed, unchangeable value, like setting a wall to a specific temperature.
If we set that Dirichlet condition exactly to 0, we create an absorbing boundary. Any material that touches this edge is instantly deleted from the system. Alternatively, a Neumann boundary condition locks the gradient. This dictates how material reflects off a wall, or prevents thermal energy from escaping the system. Without boundary conditions, governing equations remain theoretical. By locking down the edges, we establish a computable environment. Before we hand this model over to a solver, we have to strip the physical units, like meters or seconds, out of the math. Through a process called non-dimensionalization, we extract the characteristic scales of length, time, and concentration directly from the equation. This equation reorganizes itself to expose critical dimensionless numbers, specifically the Pecnet number and the Damcolor number. These specific numbers act as a diagnostic readout. They tell the algorithm exactly which physical processes, like advection or reaction decay, dominate the system. If a dimensionless number is small enough, its corresponding physical effect is negligible. The computer can safely ignore that entire term, saving massive amounts of processing power. Non-dimensionalization translates physical intensity into a strict hierarchy of computational importance. Our final task is converting continuous physics into discrete algebra, so a computer can iterate the solution. We translate the system into the standard linear state space form. The math collapses into a clean matrix equation. Matrix A stores the system's core physical dynamics, while vector B holds the external controls. This links the theoretical math directly to programmable code. By calculating the eigenvalues of matrix A, the software instantly proves whether the simulation will reach a perfectly stable equilibrium or violently spiral out of control. We started with an abstract mathematical void. We applied universal laws, defined material behaviors, locked the physical boundaries, and translated it all into a discrete matrix. By mastering this systematic formulation, we stop merely observing the physical universe. Instead, we use these governing equations to architect it.